In this lecture, we will study the small signal transfer function and the Laplace transform. This is the groundwork of AC analysis. Resistors, capacitors, and inductors are the most important passive components in electronic circuits. We have studied them in previous lectures, so now we just briefly go over them and go over the key points here. As you can see, they are in different sizes, shapes, and colors. In addition to through-hole parts, we also have surface mount parts and even chassis mount parts available. For circuit analysis in frequency domain, we usually write their impedance in S variable as Laplace transform. Then, we solve the S variable equations using Ohm law, KVL, and KCL. Just to recap, the impedance of resistor just R itself. The capacitor impedance is 1 over SC, given 0 initial voltage. The inductor impedance is SL, given 0 initial current. Now let's start with a very simple example. By doing this exercise, we will get familiar with small signal transfer function and the Laplace transform. Let's continue the design of a low-pass filter. At the input, we have 1 kHz signal in series with 100 kHz noise. So the target is to filter out the 100 kHz noise at Vsen pin with attenuation at minus 60 dB. So that means the gain of Vsen over Vin, we define this as a transfer function at 100 kHz should be 0.001. It equals to minus 60 dB by this magnitude to dB equation. The sensing gain by this voltage divider R1 and R2 is 1 over 10. So using the same equation, we can see that the voltage divider has given you about minus 20 dB already, because this is 1 over 10. So the question is, we need to find C1 so that we can have another minus 40 dB of attenuation. So in total, we will have minus 60 dB at 100 kHz. There are several steps. The first one is to choose R1 and R2, which has been done in previous lectures. The step 2 is to find the transfer function of Vsen over Vin in S variable, which is in frequency domain. The last step is to find the capacitance of C1 based on the transfer function. To find the capacitance C1, we should go to the second step, which is to find the transfer function TF of Vsen over Vin. Now we need to derive the Laplace transfer function of the low-pass filter, also known as the transfer function of the voltage gain Vsen over Vin. As we said before, we replace every passive component using their impedance in S domain and use KVL, KCL, or Ohm law to find the transfer function. It requires some algebra to complete it. Most of the time it's pretty straightforward. Now I will introduce 4 different methods to solve the problem. You can use any of them depending on your own preference. The first one is derivation by hand, requiring some algebra. The second one is Thevenin equivalent circuit by observation. The third one is coding using Octave symbolics or Matlab symbolics. The last one is using another engineering tool called MathCAD. The first one is to derive the equation by hand. So this is the schematic of the circuits. We have a voltage divider R1 and R2. R2 is in parallel with C1. So we look at R2 and in parallel with C1. So the impedance is R2 just in parallel with 1 over SC1. This is the impedance of the capacitor C1. And this is a very important network. So we got some algebra here equals to the denominator is simply R2 plus 1 over SC1. The numerator is R2 times 1 over SC1. And by algebra, we can see this becomes R2 over 1 plus S times R2 times C1, because we times SC1 on both top and bottom. So now the Vsen, that's the output, a function of S variable over Vin equals to R2 in parallel with S over SC1, this part. This is simply another voltage divider. So R2 in parallel with SC1 plus the total impedance, because this part is in series with R1 equals to, so we put this one part here to replace R2 in parallel with C1. Now we got R2 over 1 plus S times R2 times C1. The denominator is, put the same thing here, plus R1. To further simplify the equation, top and bottom we will times this part, and the numerator becomes R2, the denominator becomes R2 plus R1 times 1 plus S R2 C1. Finally, we got R2, the numerator, and R1 plus R2 plus S times R1, R2, and C1. As we did before, we got the transfer function of Vsen over Vin. So now we want to manipulate it into the canonical form. So canonical form is like this. We got the DC gain as J0. So DC gain in our case is this part. So this part we manipulate it as the canonical form. So this one will match the canonical form, and we see the G0 is R2 over R1 plus R2, and omega P will be this part, and omega P will be R1 times R2 over R1 plus R2 times C1. We can further simplify it. So omega P will be like R1 in parallel with R2 and times C1. So this is in the canonical form, which gives quite a lot of information. The first one is the DC gain G0, and the pole location omega P is determined by R1 in parallel with R2 and then times C1. So unit will be in radians per second. If we want to put it in hertz, we need to divide it omega P by 2 pi. Now we got the frequency Fp. That's the pole in frequency units. Now the transfer function has been derived. We found it here. And we know the DC gain and the pole location already. We will use it in the third step. Another method to find the transfer function is to use the Thevenin equivalent circuit. It is a pretty useful method. It says that any linear circuit containing several voltages and resistance can be replaced by just a single voltage and a single resistor in series with the voltage across a load. So we have a two-terminal circuit as this. This is also called a linear network. So we can manipulate the voltage source and resistor here to change it into a single voltage source in series with a Thevenin equivalent resistor. Notice that this method only works for resistors, not capacitors or inductors. Now let's use the Thevenin equivalent circuit. So we have the two-terminal circuit by R1 and R2. So using the Thevenin equivalent circuit, the Thevenin voltage VTH is the open circuit voltage at the terminal, and RTH is VTH divided by the current when the terminal is short circuit. Now let's find VTH and RTH. By definition, the VTH is the open circuit voltage at the terminal. Assume this terminal is open. Now this is the voltage divider voltage. It's Vin times R2 over R1 plus R2. Now we need to find the RTH, the equivalent Thevenin resistance. So that is VTH divided by the current when the terminal is a short circuit. We call it the short circuit current, ISC. When this one terminal is a short circuit to the ground reference, we see the current will be Vin over R1 only. So this is the short circuit current. Finally, the Thevenin resistor RTH equals to VTH over ISC. We got R1 times R2 over R1 plus R2. We can tell that this is R1 in parallel with R2. So now we found VTH and RTH. So the network in this rectangular can be replaced by Thevenin equivalent circuit, and then we can study the effect from C1. At DC, that means S equals to 0, the capacitor is open. Now we look at this point, so this will be VTH. So VTH equals to Vsen equals to Vin over equals to Vin times R2 over R1 plus R2. So this will be the DC gain J0 as we found before. No problem with that. So now we need to find the pole location. We know that the pole omega p is related to the time constant of the system. For example, the RC time constant. So the R will be R Thevenin resistor RTH, and this C is only the C will be C1 in our case. We know that the transfer function will be like in the canonical form. The DC gain has been found as R2 over R1 plus R2, and omega p is the pole location, which equals to RTH times C1. Finally, we got R1 in parallel with R2 times C1. So this is exactly the same result as we found before. So by using Thevenin equivalent circuit, we can just find the result by observation without the algebra. The third method to find the transfer function is to use symbolics by either Matlab or Octave. So by using Matlab or Octave symbolics, we can define a parallel function first. I usually use it with different symbolics because it makes my equation or makes my code more elegant. So we define a parallel called PARALLEL, R1 or R2. So the return value is simply R1 in parallel with R2. Now we go to symbolics. So this is Octave Online, which is a very powerful and convenient tool to calculate your equations. This is the M function I've used for different projects. So one of them is a parallel.m. This is a function of parallel. And if we go to this file, so this is the symbolics for our case. First we load the package for Octave called pkg load symbolic. This only works for Octave. And then we define some symbolics like variables r1, r2, c1, and s. We define a transfer function TF as parallel of r1, the parallel of r2 and 1 over sc1 divided by r1 plus the parallel of r2 and 1 over sc1. And then we can simplify the equation using simplify. So we run the code. You can see that this is the initial transfer function, and by simplifying the transfer function, we got the same equation here. Now let's go back to the slides. We got the same equation here. Basically, this is the result. We can only go this far, and to derive it as the canonical form, we need to do the same thing and do it by hand. So this is a very useful symbolics tool which is compatible with Matlab. Please go to this website to study it by yourself. The last method is to use another engineering tool called MathCAD. So in MathCAD, we can define a lot of things, and different from Octave or Matlab, there's no code. You run it instantaneously. So you don't need to compile or run any code here. So now we define a parallel function as here. So it makes our equation more readable. So the transfer function will be R2 in parallel with 1 over sc1. This is the numerator. And the denominator is R1 plus this part. So using the simplified equation, we can get the same result as we did in Octave and Matlab. Basically, this is the result, and still we need to derive it by hand to get the canonical form. We have introduced 4 methods to accomplish step 2. Now we need to go to step 3, that is to find the capacitance of C1 in the low-pass filter. We know that the DC gain of G0 has 0.1, which equals to minus 20 dB. Because our goal is to find minus 60 dB attenuation at 100 kHz. Because we have minus 20 dB contributed by this DC gain, another minus 40 dB will be given by this single pole. And we know the pole location by R1 in parallel with R2 times C1. So because of minus 40 dB, we can define the pole location, and we know R1 and R2. Finally, we can find C1. When the frequency omega is higher than omega p, which is the pole location, in this case, the transfer function can be simplified as G0 over S over omega p. By some algebra, we know that it equals to minus J times G0 times omega over omega p to the power of minus 1. So for further simplify it, we can get this to represent the transfer function. We look at the magnitude, we will see that the magnitude of this transfer function will be G0 times F over Fp to the power of minus 1. If the frequency F equals to 100 times Fp, then the magnitude will be written as this, and this part will be written as 0.01 times G0. So if we converted the magnitude to dB, this will be giving you minus 40 dB, plus the magnitude of this part is minus 20 dB. So that in total you got minus 60 dB. So in value, in decimal, it will be 0.001 as we expected. The conclusion is this equation indicates that the slope of magnitude in dB in Bode plot is minus 20 dB per decade. It indicates a single pole as well. The pole location in the low-pass filter is chosen as 1 kHz, which is 2 decades above 100 kHz. Because this 2 decades away, the pole will give you minus 40 dB at 100 kHz. So finally, we can find the C1 as 17.7 nanofarad theoretically, because we know that the pole location is 1 kHz. We put it back, and we know the R1 in parallel with R2 gives you about 9,000 ohm. We can find C1 as 17.7 nanofarad. I put this value here. We run the transient simulation. So this is the input voltage, and this is the Vsen. We can see Vsen is much cleaner than before because of the C1. The second observation is that Vsen is slightly lagging Vin because of this pole causes some phase delay. So now the question for you is, where does the 100 kHz noise go? Think about this question. So if we look at the Thevenin equivalent circuit, we see that at 100 kHz, the impedance over C1 is so small, so that the voltage sensing gain of this part over RTH is very small, so that the Vsen doesn't have much voltage drop from Vin at 100 kHz. This is why very little 100 kHz component occurs C1 at 100 kHz. We can check the Bode plot using Matlab. This is the magnitude and this is the phase. So this is the transfer function of the low-pass filter. This magnitude is minus 20 dB, which is our DC gain. And at some point, we can see that the magnitude becomes smaller and smaller, and it has a minus 20 dB per decade as the slope. The second plot is the phase, and at this frequency, we can see this is minus 45 degree, and before that, there's very little effect of the pole, so that there's no phase delay, and the phase is 0 degree. And after that, we got minus 90 degree. So this is the Bode plot of the single pole system. When we talk about minus 3 dB, so this minus 3 dB point is minus 3 dB of your DC gain. For example, our DC gain in this case is minus 20 dB. So we minus another 3 dB equals to minus 23 dB. In this case, we found the frequency equals our pole location, which gives you about 1 equals to 1 kilohertz. This is the source code for Matlab. Further verification in LTspice. This is the schematic in LTspice. We put C1 here. We run the transient simulation and we zoom in. We compare the input and output peak-to-peak voltage, which is corresponding to the 100 kHz noise. So this is the 100 kHz noise response, and this is 100 kHz noise input. And we can see that the signal attenuation is this number, which equals to minus 60 dB. How to get here? We measure the voltage from peak to peak equals to 3.8377 millivolt, and this peak to peak is 4 volt. So this is the attenuation at 100 kHz noise. We got this number, which approximately about minus 60 dB. This matches with our Laplace transform function. By FFT in LTspice, we can see that the 100 kHz noise is basically moved out from the Vsen. It's greatly attenuated, about minus 60 dB. So the only dominant part in the Vsen is the signal we want, which is at 1 kHz. This is just a side-by-side comparison in FFT result. Before adding low-pass filter, we have significant amount of 100 kHz noise at this part. By using the low-pass filter, 100 kHz is greatly attenuated, about minus 60 dB. To recap, we have studied the Laplace transform of R, L, and C. We go over a design example of a low-pass filter using R and C. We derived the transfer function using 4 different methods. Knowing that, you should be able to solve any RLC circuits using Laplace transform. We have studied the Bode plot using Matlab, and we verify it in LTspice in transient simulation and FFT result. Thank you very much. See you next time.